Hey, it's Dr. Sweeney from Math All Day, and I wanted to let you know that this particular video is going to be one of my lecture videos, one that I generally give to my students instead of my classes, in order to introduce them to logic circuits. It's a longer video, and as such, I cover a lot of different topics inside of logic circuits. And if you don't have any background in logic circuits, you may want to watch the whole thing. On the other hand, if you do have some background in logic circuits, kind of understand them, and you're looking for smaller pieces, you can actually take a look at some of those smaller pieced out videos where I go into particular skills that have to do with logic circuits. So a logic circuit is used to generate a pictorial representation of a Boolean function, or basically a graph of a Boolean function. As such, what we're going to do is we're going to construct functions from circuits and circuits from functions. And we're oftentimes going to be able to evaluate values for functions utilizing circuits. And some people actually find it a lot easier to use circuits in order to evaluate functions. We'll start out with some basics. And the basics are what we call our gates. Our gates represent operations in Boolean algebra. There are three of them. We've got OR, we've got AND we've got the inverter. And each one of them is going to represent or be the equivalent of a Boolean operation. The first one, OR, is going to be equivalent to AND, which makes sense because in logic, OR and in Boolean operations, addition are equivalent operations. So if we have X and we have Y as our variables, and we utilize this OR, which kind of looks like an arrow, we're going to get X plus Y. Our AND, which looks like a half circle, is going to be the equivalent of multiplication. And again, same idea here, because in Boolean algebra, and the multiplication are going to be equivalent operations. So we got X, we got Y, there we go. And then we're going to have our inverter, and our inverter is going to be the equivalent of taking the complement. So those are our three gates, and we're going to utilize those three gates in order to represent the entirety of our circuits. Next up, we have to describe an order of operations for the use in circuits. Now, the order of operations in circuits is a lot more straightforward than it is in Boolean algebra, and it's one of the reasons why people like to use circuits in order to evaluate functions in Boolean algebra, because basically what we're going to be doing is we're going to be reading our gates from left to right. We're going to begin with using the farthest most left gate and continue to the farthest most right gate. So like take for example this gate, this circuit, we've got X, we've got Y, and then what we're going to do is we're going to invert X, we're going to end up with X bar, and we'll notice that there's no inversion on the line that goes with Y. So this becomes Y, and now we'll use our OR gate for X plus Y, X complement plus Y. So notice we take the complement first, okay, because it's further to the left, and then we do the addition afterwards. If we have a line that branches past a gate, it indicates that we'll be using the result of that gate as an input for the next gate. So like say for example, we have this particular circuit, we've got X, and then we're going to get X bar past this line, and then we'll have Y, and Y, you'll notice this line is the straight line coming out from Y. We can tell that the line that is coming down past the Y line has to do with X bar because of this little bump right here. The little bump tells us that it's not Y that we're referencing, it's kind of like we're jumping over Y, but instead it's going to end up being X bar. So this circuit here is going to take X bar and Z. So now I have X bar and Y, I'm going to use both of those and multiply using the AND gate, and then X bar and Z, and then what I'm going to do is, because my lines are coming out of those AND gates, my result X bar Y plus X bar Z. So what we'll do now is we'll utilize that notion of taking the product of one gate to become the input of the next gate in order to actually generate how it is that we represent, say for example, the multiplication of three terms or more terms, or the addition of three or more terms. Because it turns out that we can't use a single gate to represent an operation on more than two variables. So if we want to represent the addition or multiplication of three or more variables, we're going to have to utilize at least two gates. So I'll give you an example. Let's say, for example, what I want to do is I want to write X, Y, Z. And so what I'm going to do is I'm first going to multiply X and Y together using an AND gate. So I'm going to get X, Y. And now for this next AND gate, the two values that I'm going to be adding together are going to be X, Y, and Z. So I get X, Y times Z. I'll do the same thing with my AND. So say, for example, I want to add together, I want to get X plus Y plus Z. So what I'm going to do is I'm going to take X plus Y first. I'm going to use that OR gate for X plus Y. And then I'm going to take z and I'm going to add it to x plus y. So I get x plus y plus z. And what you can see is that this is kind of like how parentheses work inside of Boolean algebras. Is essentially we're going to do something first. We're going to do the thing that's to the left first, and then we're going to utilize that as the variable for the next operation. So let's look at some examples. Let's say, for example, I have this particular circuit, and I'll start with a 0 here on this line, a 1 on this line, and a 0 on this line. And so we don't always have to utilize variables. What we can do is we can just assign one of our zeros or ones, or ons or offs. And so let's say, for example, I take this and I'm now going to invert. And so this is going to turn to a 1. And then I'm going to get a 1 all the way over here going to this AND gate. But then what I notice is that I've got a branch coming off of the 1, and then it comes into an inverter. So this becomes a 0. And then I have another 0. So now I'm basically at the second gate on each one of my lines. Now I'm going to take the AND gate, 1 times 1, that's going to give me 1. And then I've got 0 plus 0, that's this one here, and it gives me 0. So 1 times 0 is going to end up being 0. So this gate evaluates to 0 with the inputs of 0, 1, and 0. We could take a different look at, let's say, for example, I selected instead of 0, I picked 1. I had 1 again, and then let's do 0. So now I take 1, and I use my inverter, I go to 0. I continue to have a 1. So now 0 times 1, that's going to give me 0. 1 inverted gives me 0. And then 0 takes me down to 0. That addition gives me 0. And then when I use the AND, I get 0 again. And so that's the result of this particular circuit when I use 1, 1, and 0. The question is there anything that actually would, say, for example, make this satisfiable? And we could take a look here and kind of figure that out. One is that we need, for both of these terms from the circuit, we need both this value and this value to both be equal to 1. So what that means for me is that both of the terms here, taking one step backwards, are going to have to evaluate to 1. And so we'll use 0 and 1 as our inputs. And then what I'll need is I'll at least need 1 here. So I'm going to use a 1 for, say, our z term. There's a 1. So now the inversion changes to a 1. I get 1 times 1, that equals 1. And then I'm going to get a 0 plus 1, and that equals 1. Now I get 1 times 1 again, and that gives me 1. And so actually we can go out and find ourselves values that will have this circuit or its equivalent Boolean function evaluate to 1. So it turns out that this is satisfiable. Let's take a look at this gate. Let's say, for example, that I evaluate at 0 and 0 and 1. So I begin, I've got 0 times 0, that's going to give me 0. And then what's going to happen here is I'm going to move down this line right here, this line that I'm illustrating. And so consequently, this value right here is going to end up being a 0. But then I'm also going to invert the 0, turn it into a 1. Now, this third line down, this one right here, is going to end up becoming a 1. So I have 1 plus 1, that's going to give me 1. And then I'm going to notice that 1 is going to come down. It's going to move and become part of this line. So it's a 1. We now have the AND gate that's going to evaluate to 0. And then we have 0 plus 1 that ends up equaling 0. Or excuse me, ends up equaling 1. 1 plus 1, 1 plus 0, excuse me, equals 1. And there we go. Choosing different values. Let's say we have 1, 1, and 1. We have 1 times 1 is 1. That value now, again, moving down along this line is going to give me a 1. And then we'll use the inverter. We're going to end up 0 here right before that AND gate. So we have 0 and 1. We'll add that together to be equal to 1. We'll have 1, and this second line becomes a 1. So 1 times 1, that gives me a 1. And now 1 plus 1, that equals 1. So the evaluation of our gate, in fact, is 1. And since it actually does have values that evaluate to 1, it is, in fact, also satisfiable. All right, so now what we're going to do is we're going to write our logic circuits as Boolean functions. So instead of having zeros and ones at the beginning of our lines, we're going to have variables. Let's say, for example, we use x, y, and we've got z here. So first, what we're going to do is we're going to go from left to right, and I'm going to first go in, say, for example, I'm going to invert. This is going to become x bar, and this will become y. Then I'm going to notice that I have a branch coming off of y, and then it gets inverted, so this is going to become y bar. And this last line will become z. Now, going from left to right, I end up with x bar times y, and I end up with y bar plus z as that second gate. Now what I'm going to do is I'm going to actually multiply together these two, one the midterm and then the sum, so that I'm going to get x bar y times y bar plus z. And that is the Boolean function for this particular circuit. We'll take a look at another example. And let's say, for example, we have this one. We have x, we'll have y, and we'll have z. So we're going to have x and y, so it's xy. And then we'll have z, and you'll notice that z moves all the way down to this AND gate. But then you'll notice that xy, we're going to invert xy, so we're going to get xy bar, the xy bar for the entirety of xy. And then we're going to move xy down to below the z bar, and it's now going to become part of this AND gate here. So it's going to end up being xy. And notice that it's xy and not xy bar because it's before the inverter, right? So that's really important. Now we're going to take a look at this next line, and we'll see that it's just straight z, so this is going to become z. Now what I'll do is I'll go to the next set of gates. I have x bar y plus z, because there's an addition there, and then I'm going to have z times xy, or xyz, it's up to you, because they are commutative. So now what this gives me is I'm going to get an and, I'm going to get xy, or xy bar plus z plus xyz. And that is the Boolean function. Notice a couple things that are really important is to follow along going strictly from left to right, okay, our circuit. And make sure that if you have a line that comes past the inverter, that you actually include the inversion inside of that particular term. Let's look at a little bit more complicated logic circuit. So let's say, for example, we've got 4 variables here. We have x, y, z, and we'll put in a w here. And so what we're going to do, again, we're going to go left to right. So this is going to become x. This will become y bar. And then I'm going to actually notice that my y bar comes down, and it's going to become part of this particular gate as well. So here's my y bar there. Z is going to come across. I'll have z come straight across. And then I notice that I'm going to branch off and then invert z as well. So there's my z. And then w is just going to come straight across. It's only going to be used at the last gate. Now, what's going to happen is I'm going to get x, y bar utilizing this AND gate. And then I get z, y bar using this AND gate. Or y bar z, it's up to you. And then I'm going to use another AND gate, this second AND gate right here, and that's going to end up giving me x, y bar z. And now I'm going to multiply all of these together. I'm going to get x, y bar z, z, y bar. Now, you may notice actually that there's some simplification that we could do there, and we'll do some simplification later utilizing our laws of Boolean algebra. That's actually going to simplify the gate quite a lot, make things a lot easier for us. But for right now, we just want to see, okay, this is what I'm going to end up with. And now I'm going to just multiply at the end. I'm going to get x, y bar z, z, y bar w. And that is my Boolean function without any kind of simplification involved. Now we're going to transform our Boolean functions into circuits. So let's say, for example, I'm given a Boolean function, and what I want to do is I want to rewrite it as a circuit. So it takes a little bit of thought, and sometimes it takes a little bit of a trial and error. But all we really want to remember is that if we have, say, for example, I've got two terms, say x here, x bar, x and y bar, and I have y and z, I'm going to be adding together these two minterms at the end. And so my last gate is going to be an addition gate. So that's what I'm basically thinking about here. At the end, I've got the addition gate, which will be represented for x, y bar, and yz. So I'm going to need to back that out. And if I consider what's going to happen if I back that out, I'm going to have the multiplications. I'm going to have that xy bar, and I'm going to have the yz. So I'm kind of going backwards here with developing my circuit. And then what I'll notice is I'll actually notice, okay, well, I've got y and y bar. Those two are literals of each other. That is, one's a complement of the other. And so on the one hand, I'll just have x, because x is my only term, and then I'll have a y. But then what I'm going to need is I'm going to need to branch off of y to get the second y. Now notice, and what we'll do here is we'll actually add the inverter after the fact. So I've got the inverter here to give me the y bar, that will allow me to get x, y bar. And then you'll notice, because the line comes before the inverter, this next line will just give me y, and I can use that in the second addition, or second and, excuse me. So I got y, I got z, and we don't do anything to z, so we're just going to have that go straight back. So you can see what I've got here now is I've got x, I've got y, we invert y to y bar, use the AND gate to get x, y bar. Then I have z, and I have y branching off of the y, so I get yz, and then I'll do my addition x, y bar plus yz. And there's my gate. Let's take a look at another example. Let's take a look at this example. Let's say we have x, y, z times x plus y plus z. Now my last gate here, for example number 2, is going to be an AND gate, because we'll notice that we've got a multiplication. We've got essentially two variables, x, y, z, and x plus y plus z, and we're going to be multiplying the two of them together. So at the end of my circuit, I'm going to draw that AND gate. Then what I'm going to do is I'm going to think about, okay, well, how do I get x, y, z, and how do I get x plus y plus z? Now, if you remember, we talked about the fact that if we wanted to add 3 values together, we're going to need 2 gates. And if we needed to multiply 3 values together, we're going to need 2 gates. So we're going to actually kind of think along those terms. On the one hand, I'm going to have this AND gate. And I want, as the result of my AND gate, I want it to be, my AND gate. And as the result of my AND gate, I want it to be x, y, z. So what that tells me is that I'm going to have another AND gate before it. That's going to be my x, y AND gate. And then we'll just have going back straight to z. And then over here with our ORs, I'm going to have I'm going to have the big OR gate, which is going to add the 3 together. That's going to be x plus y plus z. Okay. And then before that, I'm going to have another OR gate to get the first 2 additions. And we'll have that first 2 additions be x plus y. So now we got z. We'll just put z down here. We'll have a second line for z. And then we'll have, coming down to this next OR gate, and we'll have the y coming in for this other OR gate. So what we can see now is we're going to get x times y. So x and y, that's going to be xy. And then we have z, so this is going to give me xyz. It'll allow me to multiply those 3 together. Then I've got our z here, okay? And I have x following this line, and y following this line. So I'm going to add the 2 of those together, get me x plus y, and then I'll add the plus z at the end to give me the 3. Now, we multiply those 2 together, I get x, y, z times x plus y plus z. And that's how we transform that Boolean function into this particular circuit. Let's consider one more function. And let's say, for example, I have x bar plus y bar plus w plus z bar. So now, I'm going to kind of look at the end, and I'm going to notice that I have an AND happening at the end. So that not AND, but OR. So I'm going to notice that I have an OR. And there's my OR. And what's going to come off of that OR is going to be this x bar plus y bar and the w plus z bar. So if we look, that means that we're going to have inverters coming before that OR gate. And then what I'm going to do is I'm going to have an addition. I'm actually going to have 2 additions, because those are the ones inside of the parentheses before we go in and we actually find their complements. And there we go. And what we'll notice here as well is that we're going to invert x and we're going to invert y. But we're not going to be inverting w and z. So now we'll check our gate. We got x bar, we have y bar, we have the addition x bar plus y bar. Then we'll go in, we'll invert, we'll get x bar plus y bar. And then we'll have w plus z at the bottom here. We'll invert that, we'll get w plus z invert. And then finally, our last OR gate is going to give me x bar plus y bar plus W plus Z bar. And so this is our logic circuit. A general principle when you're going from turning from Boolean functions into logic circuits is to actually start at the end. Take a look at what the last thing that you're going to be doing is, and then design your circuits backwards. So like kind of think about, all right, what I want to end up with, and then I'm going to backwards design my circuits. So this gives us the basics of working with circuits and utilizing them in order to evaluate Boolean functions. Hopefully this was informative, and you might actually see, you know what, I prefer to utilize circuits in order to evaluate Boolean functions because it's so easy to kind of read them, to kind of follow along in a particular order. And it also helps us to visualize these Boolean algebras as well. As we go in and we talk more about circuits, what you'll see is that these foundational skills, the better we are with them, the easier it is to understand some of those later concepts. So remember, we've got three gates. We've got OR, which is addition, AND, which is multiplication. We got inverters, which is the complement. When we read, we're going to evaluate a circuit from left to right, with the value of the variable being the result of the immediately left gate. So what we have is we have gates that are, we have terms that are the products of multiple gates. And remember, we can have the same variable show up in more than one gate. We've just got that little loop that's going to hop over the line. If we want to add or multiply together three or more variables, we're going to have to use more than one gate. In fact, if there are n variables in the term, then we're going to need n minus 1 gates. In order to write a Boolean function as a circuit, we're going to work from the last evaluation in the order of operations, then work backwards. So you'll draw the last gate first and the variables last. I hope you enjoyed this mini lecture on the basics of circuits, how do we draw circuits from Boolean algebras, and how we create Boolean algebras from circuits. If you did enjoy the video, go ahead and click on like. If you have any questions or you have any comments, go ahead and click on the comment button. And if you like some of the work that I'm doing and you want to actually see more of these as I put them out, whether or not they be in differential equations or linear algebra or discrete functions or any of the things that kind of expand off of there, including proof, go ahead and subscribe to the channel.